In this video, we're going to look at imaginary numbers. Up until now, all numbers we've looked at have been real. And we kind of looked a little bit about imaginaries, or what type of numbers might be imaginary, when we looked at our discriminant test. And the discriminant test is going to be really helpful when you're solving to figure out if you're going to get real or imaginary numbers. But an imaginary number is just when the negative appears under your radical. So the square root of -1 is the most basic imaginary number. In the past, we looked at breaking down radicals like square root of 16. Well, the square root of 16, you all know, is just 4. But now we're going to look at, well, what about the square root of -16? What is that? Well, what I can do is I can rewrite it. If you think about how we break down radicals, it's the same thing as the square root of -1 times 16. So it's the square root of -1 times the square root of 16. So the square root of 16 then is just 4 times the square root of -1. That is a perfectly fine way to break down your imaginary number. Now, we don't usually write it as the square root of -1. What we instead do is write it as I, and this is called a unit imaginary. The unit imaginary is our I, and I is a number whose square is -1. Now you may think, why are we dealing with imaginaries? Aren't we just working with real numbers? Well, that's okay, but an imaginary number times an imaginary number is a real number. Because I is a number whose square, so if I square I, is -1, which means I itself is the square root of -1. So whenever you see an I, it's the same thing as the square root of -1, or anytime you see the square root of -1, it's the same thing as I. So this is part of the reason we actually work with imaginary numbers, is you use them when you start multiplying most of them together. So this is a specific case with your unit imaginary. So therefore, if x, using the general case, if x is a non-negative real number, then the square root of -x is I times the square root of x. Again, because I can break it apart into the square root of -1 times the square root of x, which is just I root x. So now you're going to use this in your problems whenever you're solving. There's still no x-intercepts if your discriminant's negative. However, if we're just solving a problem, we can get a solution. It's a non-real solution, which we call an imaginary solution. Then we will be able to break those down. So this might be something that it'll look like in your quadratic formula. So you'll see the following, and you will have to simplify 10 plus and minus the square root of -16 over 2. So this will be something that'll come up in the quadratic formula when you're solving your quadratic equations. So you have to break apart the square root of -16. So we already said that's 4 times the square root of -1, which is I. So substituting that back in, 10 plus and minus 4I over 2. And now we simplify this across, pull out what you can in the numerator. I can factor out a 2, and I'm left with 5 plus and minus 2I, and that's all divided by 2. 2's cancel, just like when we deal with real numbers. And I get the following solution. 5 plus and minus 2I. This is a good example of a complex number. If you think back to when we talked about complex numbers deal with all numbers, every single thing, real and imaginaries. A complex number has a real part and an imaginary part, which makes up the complex number system. So sometimes when I'm just looking at imaginary numbers, my real part might be 0. And if I'm looking at a real number, then my imaginary part might be 0. But all of them fall under the complex numbers category. So a complex number is always in the form A plus BI, real part plus the imaginary part. Always put the real part first. And with our complex numbers, we will look at what are called complex conjugates. Now, I think this is the first time we've actually talked about conjugates in this class. They come from your quadratic formula, part of it at least. So the number A plus BI and A minus BI are complex conjugates. And the reason they're complex conjugates is a complex conjugate, the only part that changes is the sign of the imaginary part. And we're going to look at what happens when I do different operations with complex conjugates. Some nice things will take place along the way, which will help us simplify with our imaginary number system. So a complex conjugate just changes the negativity of the I factor. So just a couple of quick little examples with that, just practicing the complex conjugate. So what is the complex conjugate? Just listing. So the first one is 2 plus 3i. The second one is 4i. And the third one is 3 minus 6i. So the complex conjugate changes just the negativity of your imaginary part. So the first one, it's complex conjugate, 2 minus 3i. The second one's complex conjugate, negative 4i, even though there isn't a real part. And my third one is 3 plus 6i. It strictly changes the imaginary part of it, the sign going from positive to negative. We're going to work with i's. We're going to multiply them together multiple times. Again, when you multiply an imaginary times an imaginary, you end up with a real number. And so we're going to have to break down our i's. Your exponents on I should not be greater than 1. So if I take I times I, it's I squared. But I squared isn't I squared. I squared is negative 1, as I defined initially. So we're going to have to learn how to break down our imaginaries so there isn't an exponent attached to it. Starting with the first one, I to the first is just I. I mean, there's no way to break that down. That's perfectly fine. By definition, I squared is negative 1. Keep in mind, the reason it's negative 1, I is just the square root of negative 1, and that's squared. The square and the square root cancel, which leaves you with that negative 1. So I squared is always going to be a negative 1. I cubed. Okay, to figure out I cubed, that's the same thing as I squared times I to the first. If you remember exponent properties, when bases are the same, you add your exponents. That gives you 3. Well, you know I squared is negative 1 times I to the first, which is just I. So I cubed actually simplifies to negative I. Moving on to I to the fourth. I to the fourth is the same thing as saying I squared times I squared. Well, I squared is negative 1 times negative 1. I to the fourth is 1. Best situation you can get. I to the fourth is one of the easiest things to work with. I to the fifth is just I to the fourth times I. I'm pulling out I to the fourth because I know I to the fourth is 1. So that's 1 times I, so that's just I. I to the sixth. I to the fourth times I squared. I to the fourth is 1. I squared is negative 1, so it's negative 1. I to the seventh, breaking that down, is I to the fourth times I cubed. Therefore, I to the seventh is negative I. I to the eighth is I to the fourth times I to the fourth, which is 1 times 1, so it's 1. Are you seeing a pattern? I to the first is I. I to the fifth is I. I to the second is negative 1. I to the sixth is negative 1. I to the third is negative I. I to the seventh is negative I. And then lastly, I to the fourth is 1. Ooh, that's kind of dark. I to the eighth is also 1. It keeps repeating. If I did I to the ninth, it'd be I again. So it continues to repeat. So the ones you have to remember, I is just, of course, I. I squared is negative 1. I cubed is negative I. And I to the fourth is 1. Then it repeats. It keeps going back around. So these are the 4 that you need to know. Now you don't have to just straightforward memorize them. You can always come up with them. But you're going to use them enough that you probably will end up memorizing them. So we are going to simplify a high I, such as I to the 25th. So if we need to simplify I to the 25th, that's the same thing as I to the 4th equals, I to the 4th six I to the 4ths, and 1 left over. Well, I to the 4th times itself 6 times is just I to the 4th to the 6th times that 1 I left over. Now, don't make assumptions. Think about what this is doing mathematically. I to the 4th, we just figured out, was 1. And it's 1 to the 6th. 1 to the 6th is 1 times itself 6 times. So 1 times 1 times 1 times 1 times 1 times 1, which equals, very good, 1 times I. Therefore, I to the 25th is just I. Now, you can go through this every time. I could have you simplify what's I to the 147th. Realistically, what you're looking at, how many times does I to the 4th take place there? Okay, because this is just going to be 1. The part that's important is your leftover piece. You can kind of think it as your remainder. 4 goes into that number evenly. How many times? Okay. Throw that away. Figure out what's left over. That's going to be what I simplifies to. So real quick, I'm going to have you guys do 2 of these quick. So I'm going to have you pause this, please, after I write these 2 up. Give them a chance to figure out what the answers are. So simplify I to the 55th and I to the 1,242. Okay, so go ahead and pause this. Let the students figure it out. So if I take a look to see how many times 4 goes into 55, so 55 divided by 4 is 1, bring down the 4, subtract 1, drop down your 5. 4 goes into 15 3 times, that's 12, 3 left over. That's the important piece. So I to the 55th is the same thing as saying I cubed, therefore I to the 55th is just negative I. Sorry, that's kind of a mess, but there's your answer. Same thing for I to the 1,242nd. 4 evenly goes into there 310 times with 2 left over. So I to the 1,242nd is the same thing as I squared, which is just negative 1. So again, just working on how do you simplify I down. The reason we look at I is I'm going to give you a problem. It's a quadratic equation, and we are going to solve it. And then we're going to check it. And the checking part is where we're going to break down that I. So to start, we are just going to go through and solve x squared minus 14x plus 58 equals 0. Since I'm trying to solve a quadratic equation, I can do the quadratic formula or factor it. As you know already, check your discriminant to see if you can factor it and what kind of solutions you're going to get. When you go through and do the discriminant test, you get negative 36. Because it's negative 36, I can't factor it. I must do the quadratic formula, and I'm going to get two non-real solutions, 2 imaginary solutions. Then what I'm going to do is I'm going to take one of those solutions and check it. So pause it at this time, please. Please do the quadratic formula on this problem, solve it, simplify your imaginary, and then we'll come back and go through the answers. So when I plug this into my quadratic formula, I get 14 plus and minus the square root of negative 36 all over 2. So then you have to break down the square root of negative 36. So x equals 14 plus and minus 6i over 2. Factor out the 2 across the top. You're left with 7 plus and minus 3i over 2. 2's cancel. Therefore, x equals 7 plus 3i. And then you also get 7 minus 3i. Those are complex conjugates, so that's where you're going to see complex conjugates along the way. The last thing that we always do is we always check our solutions, at least one of them. I would pick the one that's the easiest for you. If the one works, because they're complex conjugates, the other one will automatically work as well. So I'm going to check the 7 plus 3i. So here's my check. So it's 7 plus 3i squared minus 14 times 7 plus 3i plus 58, and that has to equal 0. When we check our solutions, we plug it in on our one side and we work straight down the process. So now when you go through this, you have to actually go through and do the expansion. I'm going to show this step by step so you can kind of see how the I part breaks down as well along the way. If you skip a few of these steps, that's fine. Some of you like to shortcut squaring binomials, which is fantastic. Otherwise, the rest of you do it the long way, which is perfectly fine. So here's my first part, the squaring. So 49 plus 21i plus 21i. So I'm going to combine that together into 42i plus 9i squared. I have an exponent on my I, which means it needs to break down further. I will break it down further in the end. That way I don't have to deal with it along the way. So then I'm just going to erase this. It was just kind of a placeholder so you could see it. Then I have the minus 14 times the quantity 7 plus 3i. So think about it as a plus and negative 14. So that negative 14 sends through to everything. So you get minus 98 minus 42i. And then I still have a plus 58, and that has to equal 0. So at this point, I'm going to look at combining like terms together. So I have a 42i and a negative 42i, so those cancel out. And then I have a positive 49 and a negative 98 and a positive 58. So adding those together, I get 9. And then I have this 9i squared. Oops, squared, I'm sorry. And that has to equal 0. I squared, as you already know, equals negative 1. So this now becomes 9 times negative 1 plus 9. That has to equal 0. We're kind of checking that whole equal 0 part along the way. So 9 times negative 1 is negative 9 plus 9. Yep. 0 equals 0. You checked it. It works. Therefore, it's a set containing 7 plus 3i and 7 minus 3i. And that is the solution to our equation. So you're going to practice solving and then simplifying as well, breaking down those i's along the way. Even though we have to do the quadratic formula, our problem isn't very ugly. Because it's a perfect square with the negative, that radical breaks down really nicely. Even if it didn't break down completely, if, for instance, the discriminant part was negative 48. Even with that, when you're doing the quadratic formula, you'll still be able to break this down. So say it was 2 plus and minus the square root of negative 48 over 8. Break down that negative 48. Pull out all of the perfect squares that go in there. Because remember, it's just I times the square root of 48. So you can figure out which parts go in there. 16 and 3. So it's 4i root 3. Bring that back in. You can have that imaginary sitting out front. That's perfectly fine. Factor out your 2. You get 1 plus and minus 2i root 3 all over 4. So those are some of the types of examples you'll see as well, breaking down your radicals.